We've all dreamt of it, right? Hopping into a spaceship, hitting a button, and just zipping across the galaxy. Science fiction makes it look so easy. You just dive into a black hole, or maybe find a wormhole, and boom, you're light years away. It's an incredible idea. But could any of it actually be real? Can we really bend the very fabric of space and time to explore the cosmos?
All right, let's break this down. First, we're going to talk about that big interstellar dream and why it's so darn difficult. Then we'll look at why the classic sci-fi move using a black hole is actually a fatal illusion. From there, we'll explore a much more promising, though still totally theoretical, idea, the wormhole. We'll find out the mind-boggling price we'd have to pay to build one, and finally, we'll get into the really weird stuff, the enigma of time travel itself.
So, first things first, the dream. And this dream, well, it immediately slams headfirst into a very, very big wall. And that wall is the universe itself. It's just unbelievably huge. Which really brings us to the core question here. Is it actually possible to journey to another star system within a single human lifespan? Or are we kind of stuck here in our own little cosmic neighborhood for good? Here's the brutal reality, thanks to a guy named Albert Einstein. The speed of light isn't just a suggestion, it is the absolute speed limit of the universe. To get to our closest stellar neighbor, Proxima Centauri, our fastest probe would take more than 50,000 years. Even if we could travel at 99.9% the speed of light, it's still a 4-year trip. So yeah, for interstellar travel to be practical, we're gonna need a shortcut. So this brings us to the most famous shortcut in all of fiction, the black hole. We've all seen it in movies, right? A spaceship dives in and pops out somewhere else entirely. It sounds cool, but a deep dive from a University of Bologna thesis makes it pretty clear, scientifically, this idea is a total non-starter.
In fact, there are at least 3 absolutely fatal reasons why this plan is doomed from the start. First off, it's a one-way ticket. Once you cross a black hole's event horizon, there is no coming back. Nothing escapes, not even light. Second, the theoretical exit door, what they call a white hole, is incredibly unstable. It would slam shut the second you try to use it. And third, and this one's a doozy, you'd be spaghettified.
And yeah, spaghettification is exactly as terrifying as it sounds. The gravity pulling on your feet would be so much stronger than the gravity on your head that you'd literally be stretched into a long, thin strand of human pasta. It's a gruesome end to any trip. The takeaway here is crystal clear. Black holes are cosmic prisons, not cosmic highways. Okay, so if black holes are out, are we just out of luck? Does physics have a better idea? Well, it does, at least on paper. Let's talk about the wormhole. Now, this is a great way to visualize it. Imagine space-time is a giant sheet of paper. To get from one point to another, you could slowly travel across the surface. Or you could just fold the paper in half and punch a hole straight through, creating an incredible shortcut. That's a wormhole. It's a theoretical tunnel connecting 2 very distant points in space and maybe even time. But, not all wormholes are created equal, theoretically speaking. The original idea, the Einstein-Rosen bridge, was just as useless as a black hole. It would pinch shut and collapse instantly. It wasn't until the 80s that 2 physicists, Morris and Thorne, came up with a new design, a theoretical model specifically engineered to stay open and be traversable. So for a wormhole to actually be useful, it needs a few key things. It can't have an event horizon, so you can go in and come out. The gravity can't be so strong that it spaghettifies you. The trip has to be quick. And the most important part, the tunnel itself has to be stable. It has to actually stay open long enough for you to get through. And that last point, keeping the wormhole propped open, that's the big one. That's the catch. And it comes with an absolutely astronomical price tag. To hold a tunnel in space-time open against its natural tendency to collapse, you would need something that pretty much breaks all the rules of physics as we know them. And that something is called exotic matter. To put it simply, this stuff would need to have anti-gravity. See, everything we know, planets, stars, you, pulls space-time inward with gravity. This exotic matter would have to do the exact opposite. It would need to push space-time outward, acting like a cosmic scaffold holding the throat of the wormhole open. Which leads us, of course, to the single most important, multi-billion-dollar question in this whole discussion: does this stuff even exist anywhere in our universe? And the simple, direct, kind of disappointing answer is no. We have never, ever seen or found anything on a large scale that behaves this way. For now, it is completely hypothetical. But there's a fascinating little asterisk here. As this quote from the Bologna thesis points out, just because we've never seen it doesn't mean physics says it's impossible. On the quantum level, some things, like the Hawking radiation from black holes, might produce tiny, fleeting amounts of this negative energy. So the door isn't totally slammed shut. It's just that we have absolutely no clue how to make this stuff, let alone on the epic scale needed for a wormhole.
Now, if you can bend space-time enough to build a bridge between two places, that leads to an even wilder question. Could you build a bridge between two times? This is where things go from interstellar travel straight into the mind-bending realm of time travel.
And when it comes to time travel, the legendary Stephen Hawking had a very clear take on it. He was convinced that while going to the future is a proven fact of our universe, any trip to the past is fundamentally impossible. So here's the difference. Traveling to the past opens up all kinds of logical knots, like the famous grandfather paradox. Hawking believed the universe has its own self-defense mechanism to stop that from ever happening. But traveling to the future? That's just a weird side effect of relativity. The faster you move, or the stronger the gravity around you, the slower time ticks for you compared to everyone else. And this is Hawking's brilliant safety mechanism. He compared it to audio feedback at a rock concert. You know that horrible screeching sound when a microphone gets too close to a speaker? Well, he argued that natural radiation would enter a time-traveling wormhole, go into the past, and come out right at the entrance, just in time to go through it again and again and again. This feedback loop would build up energy infinitely until the wormhole just obliterated itself.
But traveling to the future? Oh, that's not science fiction. It's happening right now. The clocks on GPS satellites orbiting Earth literally run a tiny bit faster than clocks down here, and we have to constantly correct them. At CERN, when they speed up particles to near the speed of light, those particles' lifespans stretch out 30 times longer from our point of view. For them, time is slowing down. We are all, in a way, time travelers. Which leaves us with one final, fascinating thought to chew on. Are these laws of physics a kind of cosmic protection agency saving reality from the chaos of paradoxes? Or are they the bars of a cage, keeping us locked in the present, always marching forward in time? For now, it seems our journey to the stars remains a beautiful dream, hanging right there between science fiction and the absolute edge of what we know about the universe.